Okay, welcome back. So last week you learned basic about forces. Today we're gonna talk a little bit more about it. I will start from the answering your questions that you did have last week. This one, sorry, I cannot tell you what's the problem here because I cannot see what's the. But I think there. Check. Maybe I think you have some typo. Meaning of the last part, check borders. Why we check borders? Because okay, if you go here, I open Photoshop. Okay, we have our screen, right? And we have borders here. So why I do check borders? I don't want the balls. Let's get another color. I don't want my balls to go out from the screen, so I want them bounce when they trying to escape the screen. So that's why we calculate here. Okay, if this position plus mass is the mass also represents the size of the ball, less than if this position and mass this position and mass multiple minus width. So I just checking here. Okay, if it's here, but again, if I take out radius, because the position of the ball in the center of the ball, I need to calculate radius to figure out how it's gonna bounce, right? Why do we need to use force? Force is just like, okay, now we're talking about physics, force and physics, yeah? It's pretty much like straightforward. But force basically it's any force, any influence, anything. So you can think next class we're gonna talk about simulations, why we do simulations and what kind of simulations. But force that you can use for anything. It can be physics force, yeah, like wind, drag, I don't know, power, resistance. Force could be just like for time, force of life, yeah, for example, for lifespan, I don't know. You have force of hunger, you can force of laziness, you can force of anything. So force is basically anything you can apply to change the current state of the object. In our case, we talk about position now, but it's not could be just position, it could be mood. Yeah, you can apply some force to change mood. You can apply some force to change your thinking, your habit, whatever. Apply force, apply gravity. So apply force is basically this function will apply any force we have. Apply gravity. Here it's a little, we use it separate because gravity actually does not really we do not use like mass for gravity because we have like too big mass or too small mass, so we do not use the mass for applying gravity. It does not matter how heavy object, if you throw it from like roof, it will be applied the same force to this object. Okay, and one more question. It was from the Angela. It's kind of right, so I gave you so last time I give you this kind of equation, right, to apply force, and okay, it's another screen. Still another screen. So last time I showed you this equation to apply force, and Angela asked me why we use this one, because in school you learned another one. What you learn in schools, it was like position equals 1/2 from acceleration square time. Yeah, so it's gonna be a little bit different result at the end. What does we use in our calculation? Here the calculation we use, position equals previous position plus velocity, velocity equals previous velocity plus acceleration. That's what we do have in our calculation. What's the difference? This one and this one. And why we use this one for this? First of all, this can give us a little bit more simplification. First of all, when we're doing any simulation, so let me create another screen. This is our term line. Yeah, this is position. So the equation that Angela gave us, it's very useful when we're talking about kind of like long period of time. So let's just use this equation again. P equals 1/2 AT square. So all depends here from the T. So if our T1, this equation will be P equals A2 1 divided by 2 by A. So it's pretty simple. So T1, 1 second, our position gonna be this one, but we also have previous velocity, so our position should be, in this case, plus velocity, previous one. But velocity also need to represent back this acceleration. Yeah, so during this is the same time, so okay, I'll change color. V, as we defined before, it's previous velocity plus acceleration by t. This is if we have constant acceleration, but this is not for constant acceleration. But anyway, even if do like this. Our position gonna be previous plus 1 2 a plus a. So actually it's gonna be 3 2 by a, yeah, if we have constant acceleration. Again, we have a different result, and we have one more final formula, because this is if we're talking again about long period of times. So this is not gonna help us. Another formula for velocity, another equation we have, it's gonna be integer from our acceleration by time. So what does integer mean? It basically gonna be sum of all velocities through the time t. So it's this plus this plus this plus this plus this, right? So if at moment v1, v0, our acceleration, okay, 0, and our velocity at z0, at a0 gonna be 1, our acceleration at a1 gonna be 2, so acceleration at v1 gonna be 1, but acceleration at v2 gonna be acceleration from 0 plus acceleration plus 1 from acceleration from 2. It's gonna be 3 already. So this is gonna be give us integer. So if we will combine these two formula, 80 square and v equals integer from 80, at the end they will pretty much close each other. One more things we can think about it. It's over period of time, yeah. So if our t infinity small go to 0, so almost 0, if we take a measurement very often, t2, so it's gonna be very small number. So in this case, so if t0, t square also gonna be moving to 0. So our position not gonna affect by velocity in this case, or by acceleration in this case, does not matter how big acceleration, if we take in very small intervals of time, yeah. Okay, we have 60 frames per second. If we're talking about acceleration things, so this is will be 1/60th, and if we just calculate it, t square gonna be 13600. So it's a very small number, so our acceleration not gonna really affect position, so just our velocity will affect position, because again this is, it's just related to acceleration, right? So our acceleration for this period of time. Second example, if our t go to infinity, to very big number, so this is going to be also go to infinity to big number. Let's say we have like 60 seconds. So yeah, and for 60 seconds it will be affect a lot, but our acceleration also affect velocity. That's what we're doing calculation. So to simplify all these formulas, basically we have kind of convention for this simple stuff of formula. So our position is going to be our previous position plus speed, and speed already will take care of acceleration, right? So yeah, it could be a little bit messy here, but this is I just give short explanation why we use these formulas here rather than this one. Again, mostly we doing with continuous acceleration. Okay. Okay, so this is pretty much for the answers. And now let's talk a little bit more. So today we're talking about so much screens, applying multiple forces and what kind of forces. So last time we have our ball, and for ball we apply the gravity force. Okay, it's usually marked like big J, right? And no. So, and another one force we apply is, okay, let's run it. Yeah, we have this, our ball falling down. So this is pretty much, okay, it still show on another screen. Anyway, so we have gravity and we have some, so wind force, yeah, we apply. So wind is just like whatever force, any external force, basically. And we take care of mass, because for gravity we decide mass not related, but for wind we have relative to mass of the object, right? If we have bigger object, we need to apply bigger force to make it move. Today we will talk a little bit more about few different forces, so like friction force, drag force, and attractor. It's usually calling gravitational attractor. So what this force doing? Okay, friction force. Okay, if we talk about friction, for example, let's say we have our surface and we have some object that by the gravitational force will go slide down, right? But we have some force that gonna stop this object, because okay, if this surface bottom it's ice, our object will be slides very fast. But if it's rubber, or I don't know, some not even surface, stone, sand, it's gonna go down very slow, right? So this force against from surface is basically friction force. What friction force it's about? Friction force is force opposite to the force we have this object to move. So friction is gonna be minus our force but not logic, multiplied by the friction coefficient. So this is coefficient gonna be just different for different materials. Yeah, for ice it's gonna be very small, for rubber it's gonna be high, and the surface of the object that this falls upright, because friction force gonna be work based on the area. So friction coefficient, yeah, again, for example, for ice it's somewhere around 0, but for the sand it's gonna be some high, no, 0.1 for example. So that's how we can calculate our friction force. Drag force is kind of similar. So drag force is the same friction force, but it's more applying to the whole object. Usually it's talking about the environment. So if we have water, our object inside of water will move slower than our object in the air, right? Because water have consistency, water have some volume and resistance to it. So even you know, yeah, like you can run so fast when you in the water, because water applies this drag force opposite to you. Again, this force gonna be pretty much the same, minus force we have multiplied by drag coefficient and multiplied by size, the area to which this force applying. So it's pretty much the same. So if you do not do like really physics simulation for different environments, it's just like friction force applied to usually like one part of surface, drag force again it will apply to the bigger part of surface. It's more like environmental force, but you can put them together. And attractor, it's what we did pretty much before when we talk about particles. It's the force gravitational between two objects. Yeah. So again, last class we talked about the gravitational force, like attractor, it's gonna be G, it's the gravity force, object mass object 1, object 2, and divided by radius, distance between them. But yeah, in our case here we don't really talking about this one. So this one we have for like Earth, for like big object, yeah, but basically we will attractor, we have again some coefficient, attraction coefficient, we have two mass, and we have the distance between these two objects. Okay, so to build this simple simulation, now, yeah, I will go there to our project and we will just try to apply multiple force. Let's make it bigger. So what we did here, let's class, if you run, cafe jumping, and it's jumping here again, it's falling down, and we have some wind, very slow, two objects with different mass. Okay, we can. Okay, let's for now we create a little bit more objects. Random width, random height, the position, and here I will tell. Okay, I need int here. I think because my mass float, so I don't need int. I can tell, okay, random mass. Okay, let's say 10 gonna be. These two I will kill. Let's start, try and run. Okay, I still have 2. Let's say we have 5 objects. So now we have force falling down. And we have also some bounce coefficient right now. And you see the size here. Now I change the bounce coefficient to almost the same, so they will bounce like longer time. And you see how. Okay, and here let me say from 2 to 10. Okay, or 1 to 10. Do not have so small one. Okay. So now we have 2 force, gravity force. It's pretty high now, they're falling down, and wind, it does not affect much. Yeah, if we restart it, we see it's just jumping at the bottom here. So what we're gonna do now, we're gonna talk about this, add some forces. We does not really have friction force in this setup. It's minus 50 and height minus 50. So this I changed, so they're not gonna appear somewhere outside. Yeah, from 50 to 50. So this is like for beginning position setup, they not gonna be outside. We do not have friction force here, but what we will do have, we will do have drag force. So as we defined here, for drag force is basically current force we have minus some coefficient multiplied by size. So it is force that gonna push backwards. Let's try to do it. So first I need to calculate the one more vector. This is gonna be for drag force, or I can just I can use it just here, for example. P vector drag gonna be P vector 0 0 at the beginning. Okay, new P vector 0 0, right? Or I can just calculate. So you see here all our forces combined in acceleration, yeah. So for drag, I can do the same. Okay, maybe not vector. Basically, acceleration is our force, but what we have now, we need to get like our negative force. I can write minus this acceleration okay, let's do like this. Okay. Okay, I will apply this minus later. This acceleration multiplied by drag coefficient and multiplied by size. So here I will do something like this. Float drag coefficient, and let's say it's gonna be for air, it's gonna be very small. Again, I will copy it, otherwise I will change it, right? I will multiply it by drag coefficient. And it's also related to the size, but in our case, mass, it's the size. Yeah, where we draw it. Yeah, mass multiplied by 10. So this is going to be the size of the object. So the bigger size of the object, then bigger it's going to be the force. Okay, so what I do here, I have acceleration, I copy it, right? Because I don't want to change the acceleration when I multiply it. If I will use multiply to acceleration, it will change it. I multiply it by drag coefficient, it's our environment, and I multiply it by size. And now I have drag formula. And now I need to just like multiply it again by -1 because it should be negative drag. And now I can use just the same. P vector is gonna be the same force, it also will be divided on mass, then heavier object, then less this force gonna be affect him. So all I can do, I just can use this, apply force, drag. Okay, not much things change now. But for example, if I change drag coefficient to 0.2, okay, it's too big. Okay, 0.1, they stop this place. So it's like the environment, very resistance. So like 0.8. So now it's more like in water, they. For example, what I can make here, I can draw rectangle from, let's say, 0 to divided by 2 with height. So this is gonna be water. Let's just use some fill air GB. Okay, let's do like this. So this is water, and here I will create the two coefficient, drag coefficient air and drag coefficient water. So for air it's gonna be very small, and for water it's gonna be something like high. And here, when I will calculate it, I can take out this multiply from here now, and I can write if this position y less than height by 2, drag multiply by drag coefficient water else drag gonna be multiplied by drag coefficient air. So what we see now, okay, it's opposite now. If this, yeah, it should be bigger here. So if the ball here, they will move faster than they inside of water. We can make it 7 like bigger difference. So you see they even cannot get out now, they still move in the water. But so yeah, then more I will put this coefficient here. Then slower they gonna move inside. This is jumping out, this have a lot of kinetic energy. So we have something like this. We can make more of them. And when they appears, for x we can set up height by 2. So when they appears, they always will appear on the top. So it's kind of funny. And I think bounce coefficient too high. We need to make smaller. So they need to lose the energy when they're hitting anything. Okay, so now we apply drag force. You see now they're going, it's like more like in water, right? Now what next things we can do, let's apply the attraction. We already did this in the simple way when we calculate for in previous lessons about planets. Yeah, we did. We calculate the attraction between two objects. So here, so I will create the one more function, void apply gravitational attraction. So for gravitational attraction, what I need, it's gonna be mass of myself multiplied by mass of another object and divided by distance between these two objects, right? And it's multiplied on some attraction coefficient. We have this big G, it's for Earth, we know 9.8 basically. And this one For Earth it does not matter much because it's too big. Okay, how we can do it? For this I need to go through the all other elements. For e int y equals 0, I less than this n, I plus plus, and now I need to calculate. I will create one p vector attractor. It's gonna be new p vector, so each time I will calculate different, and now I will write. So first I need to get first I need to check if I it's not my current object. Yeah, for this one I need to create here one more integer id, and when I gonna initialize it, if it's random, okay, let's set up id random from 0 to some big number. It should be int. Remember, check the types. But or here I will set up the int id. This id equals id, and here when we're gonna initialize the object, we will give id y. Let's run. Okay, it's worked, no problem. So now I can check my id. If I not equals id, so it's not myself, because I don't want to check attraction with myself, right? I need to get mass and I need to calculate distance. So float distance, it's gonna be, I need two vectors, m1 and m2, and not m1, position of current, this position minus 7. We can go more interesting, we have distance function. Yeah, I can define it as this position, copy, I don't want to change it, distance with the, I need this id, so I need to get it with the objects I position. So now I get distance, and to again, usually when we do these things, to simplify it and to do like less calculation, we will create the int max attraction distance, let's say 200. So if the object's more than 200 pixels away from each other, we're not gonna calculate it, we're gonna save some time and computational power. If distance less than max attraction distance, we do calculation. So what's this calculation? I need to get this mass, right? Yeah, mass multiplied by object y mass and divide by distance and multiply. I need to create some more float attraction coefficient. Let's say gonna be 0.2. And this I need to add to utter add okay, but this is now is the force, but it does not have the direction, right? So again, you remember, if we have to force, we need to find the not the distance between them, but also direction of this angle. Okay, I will create it float power of the force. This is going to be power of the force. And p vector direction, it's going to be this position copy minus okay. I forget what the plus, not minus, sub. Yeah, I think substitute. Yeah, but again, I need copy first my vector before I substitute it. So this is direction. Let's check. It's also, I forget, p vector normal. Let's go documentation. How I can get normal of p vector, subtract right dot cross limit array angle between magnitude copy set random copy distance cross normalize. So you remember here I need to normalize it because I don't carry here how far away I carry just like what's the direction between them. And now for attribute I can add direction, but this is just direction, and I can use basically I need to just use multiply here by power of the force. And after I calculate all of them, what I need to do, I need to do this like applies force, and this force gonna be attraction. And now I need to call this function. Again, I will call this function before drag. Drag I will call at the end because it's resistance. Let's try run. So you see now they they should come closer together. So yeah, they try to keep closer. If we change attraction coefficient to bigger one, it should work better. Let's delete gravity for now. It's too messy. No, now it works opposite. So yeah, here I should use object y position minus this position, opposite direction. So you see now they getting wild, and you see here they move, and we can, let's try even bigger. So now they come together, yeah, but okay. Again, attraction, then closer they to each other, then more attraction force they will have. Okay, it's not bad. Okay, already. Let's do like this, and let's for gravity make even like smaller force. Back our gravity here. Gravity is still very big. So now we have like attraction forces, they affected more than gravity. Okay, we have something interesting, right? Already now. So next things, what we can try to do here, I think it's gonna be interesting. So first we can, the attraction force, it could be in two directions. It could be attraction or it could be opposite. So some objects, they don't want to be attractive to each other. Let's just try to do it simple, and I will create another one. Boolean. I will call it lonely. And when I will build it, I will write this lonely equals int from random. Lonely. And here it should be int. And here lonely gonna be the same. Right? And where we draw it, let's just check it. If this lonely fill 2000, okay, the lonely one gonna be red, other one gonna be green. Let's check. Okay, all of them green now. It means this stuff does not work this way. I just can, in this case I can write if random from 10 less than 5, this lonely equals false. Else this lonely equals true. Okay, red one should be lonely, green one should be normal one. And now when we calculate this one, I also can do something. I can write if this lonely I will do the power gonna be multiplied by -1. So if it's lonely, I want them to keep away from others. So you see the red one, they trying to escape each other. The green one, they will try to to get closer. Green one try to get closer, red one try to get away. Let's change here a little bit. Okay, let's change sizes. And maybe let's limit maximum speed to make it a little bit not so. Okay, now we have so much lonely objects. I can make also more of object now. Okay, you see the green ones, they trying to keep together. Red one not so. Again here, now when it's move, I can apply coefficient a little bit bigger to slow down more in the water. You see water now try to push them back more. So this is pretty much, now you see that we can use different force. We just pretty much, after we calculate the force by themselves, we just apply this force, apply wing, apply drag, and here we apply the attractor force, but we will need just calculate this drag, base it on current force, current speed of this object, and the size of this object and coefficient. And attractor, yeah, we calculate based on the all objects around. So this is pretty much everything for now. So next class we will start to talk about simulation. Next class gonna be more theoretical. Why we use simulation, what simulation, and so on. And after we will have 2 more classes to try to do something more interesting simulation. This is already pretty much simulation of physics. We also did simple like solar system simulation. So now you will see how to apply it a little bit more. So, and why we use this simulation. Okay, bye. See you next time.